Hi. So, in the previous video, we've covered complementary function of the second order difference equation. However, we were dealing with the first two cases. So the cases of repeated real roots and cases of distinct real roots. I stopped this at this moment because when we turn to case number 3, the case of complex roots, we need to use some knowledge that we kind of already have, but let's organize it properly, because here we will have a little bit different trick than in case of differential equations, of going from complex roots to complementary function. Okay, but let's set everything up. So, we've got second order difference equation, right? Homogeneous, we just care about complementary function at this moment. And we have calculated that a1 squared is lower than 4a2. This right away means that we are dealing with the case of complex roots. Okay, what do we know about these complex roots already? Well, we will have two complex roots, right? Those complex roots are given by h plus minus vi, where I, of course, stands for imaginary number. We also remember that h is nothing more than negative a1 over 2, and v is 4a2 minus a1 squared over 2. Right? This was the trick with I that allows us to deal with the complex root case. Okay, so look, if this is the case, then what is our complementary function? Well, the complementary function should go as yc equals a1, right, b1t plus a2 b2t. Right, and now we can take the answers we've got and we can just simply substitute them into the equation, right? So we've got that this is a1 h plus minus v I to the power of t plus a2 h minus v I to the power of t. And look, the thing is, these expressions look somewhat similar. However, this is not the form we were using when we were dealing with difference equations. The differential equations, right? And unfortunately, here we will have to use some different tools. This is why, before we move on to what is the last and final form of the complementary function, let's go back for a while to sine and cosine function, right? Okay, so let's now imagine that this is a perfect circle. And what do we have in the circle? Look, here we've put on this axis we've got h, right? And over here we've got v. So look, over here we can say that this is our h, and because this is a right angle triangle, right? So this side, right, the red side is called adjacent. Right? Then over here we've got v. This v stands right in front of the triangle that we are dealing with. So we're going to call it the opposite, right? hypotenuse, okay, let me just, I think we already done it, but let me just remind it. And how do we calculate? Look, we can do it with Pythagoras theorem, right? The length of hypotenuse of the square of hypotenuse, right? So r square is given by h squared plus v squared, right? But we are not interested in r squared, we are interested in r. So we can take the square root of this expression and we're going to get pi. What do we know about it? Look, this expression over here can never be negative, right? So we can say that our r is always going to be positive. Okay, so what else did we learn about trigonometry? Well, we've learned two very important things. First is that sine theta of our theta over there is simply equal to v over r, right? And cosine theta is equal to h over where's my yellow color? Yeah, over r. And look, knowing those two relationships and knowing that all those three variables all appear in a specific array, in a specific order, they are all interconnected, we can actually find that r I'm sorry, the v, we calculate v out of this is r times sine theta, right? And by the same token, out of here we get that h is equal to r times cosine theta. Okay, and look, this gives us a hint of what to do next with the expressions that we've got. Because look, now, knowing this, I can easily write that h plus minus vi is equal to what? Well, it's equal to just based on what we see over here is given by the sum and the difference of these two expressions, right? So we know that r is appearing in both of these expressions, right? So we can take it up. Let's do it slowly. So we've got r cosine r times cosine theta plus minus r times sine theta, which is equal to, of course, r times cosine theta plus minus sine theta. Okay, and look, this is leading us somewhere, right? We've got the expression that is actually a little bit easier to work with. However, this is not the end of the story. Please remember that when we were trying to find a time path and complementary function under the complex case, when we were dealing with differential equations, using Euler's relations. Okay, so what were those Euler relations? Well, we demonstrated that if you take E, number E, and you're gonna raise it to power either plus, minus, of course, I, theta, we were getting that this is equal to cosine theta plus minus I sine theta, right? This was the fundamental relationship for differential equations. That was fundamental relationship for differential equations, right? Now we're going to also use it over here. Because look, now we see that those two, now we see that those two expressions, and I'm missing I over here and I over here. I'm sorry. Those two expressions are the same. So we can go on one step further over here, right? And if we're gonna take one step further, it's gonna turn out that we've got R times e to the power plus minus I theta. Okay, so look, what we have established is that our complex roots can be expressed differently in the following form, which is actually going to tell us quite a lot. Because now, let's notice one simple thing associated with what we just found out. First, look, if I'm going to take H plus IV, and I'm going to take it to some power n. Doesn't matter what power. Look, this tells me that I'm taking to the power of n this entire expression. Right? And look, this is not all. We know all the necessary operations with exponentials to deal with this case. We know that this is simply going to be Rn times E times E, of course you're just plus, E to the power I n theta, right? And look, by the same token, H minus IV to the power of n is equal to R to the e to the power negative I theta to the power of n. So this is Rn e to the power negative I n theta. And look, these two relationships in turn are leading us towards something that's called De Morbier theorem. I'm going to spell it just once because I think I came as close as I could to this French sounding name, but we've got the Morbier theorem. Okay, so what is this theorem all about? Basically, it combines everything that we've already stated. So, if I'm going to say H plus minus IV to the power of n, so if I'm actually going to take set of complex conjugate numbers and raise them to the power of n, h plus I, v, n, so complex roots, pair of conjugating and complex roots taken to the power of n is giving us definitely r to the power of n. However, look, what we need to change in this part. Look, we just need to look what happened over here, right? When we were writing them down both separately. Now, n has slipped into our formula. So we need to take this into consideration. How do we do it? Well, look, all we need to do is actually to change this expression. We will have cosine theta plus minus I sine theta, and just look where this should go. Look, if we had, when we had this situation, this n is appearing next to theta, right? So it should be here and over here. Of course, this theorem is basically showing us how we can get to a pair of conjugate complex numbers to a given power to its expression in terms of circular functions. Now look, if I'm going to change now only one tiny detail, what am I getting here? R to the power of t cosine theta t plus minus I sine t theta t. And this is definitely something we can use in replacing the expression that we've got over here. And this is exactly what we're going to do in a second. However, before we do so, let me just demonstrate to you a couple of other, let's just say, trigonometric tricks that we haven't used thus far, however, they're going to be very, very helpful in what is to come. Okay, look, first, we remember that r is equal to h squared plus b squared, right? And we remember that h is negative a1 over 2, right? So we can easily see that if I'm going to square this, it's going to turn to this. Now, v is 4a2 minus a1 squared over 2, right? Under square root. Now, if I'm going to take this to the second power, I'm going to have 4 over here, and this is 1. And of course, all of this under root. Now, you can easily see that those two expressions are canceling each other out. All we have left is 4a2 over 4, or simply square root of a2. And look, we know that r must be positive, right? So this would suggest that in this case, definitely a2 in our equation needs to be positive. Well, if it's not, then we will not have the complex root case, right? Okay, now we can do the same things with other functions. with other expressions. So for example, cosine theta that is equal to h over r. So let's go back to our expression with h. Our expression with h is simply negative a1 over 2. Negative a1 over 2. And now look, we need to divide this by square root of a2, right? So what we get out of this is negative a1 over 2 h2. Okay, and finally, the Russ relationship states that sine theta is equal to v over r. This one is the most problematic. However, we can easily deal with it. Okay, so v is square root of 4a2 minus a1 squared over 4 divided by r. Divided by 2, sorry, I skipped one step. Divided by r, and we already found that r is square root of a2, right? Now, look, there is a very simple trick we could use here. Like, what do I mean by that? Look, 2 is 4 under the square root, right? And now, if we've got square root over here and over here, why not put everything in a square root? And look, we get, again, we get out of this that those two expressions, if we divide this fraction into two different separate fractions, we're going to get that this is 1 minus a1 squared over 4a2. Okay, we're not going to be using this a lot. However, what I definitely need you to remember is this. Because this gives us a very short and accessible way of calculating r, and as you will see, is going to turn out to be the main part of our complementary function. Okay, so now we are fully ready for the final version. Now we are fully ready for the final version of the complementary function for the case of complex roots under second order difference equation. Okay, so we now just need to continue where we started. Look, what do we have over here? Well, we said that as usual, complementary function will be made out of the exponential expressions that we know. However, because b1 and b2 are conjugate complex numbers, we needed to rewrite it a little bit. But now we know exactly how to do it. What do I mean by that? Look, now we know what will happen with this t, right? Now, we will have here a1 times r to the power of t, right? Times cosine theta t plus, of course, I sine theta t. Then, instead of the second expression, we're going to have a2 times rt cosine theta t minus sine I sine theta t. And I know that was a little bit much, but now, look, all we've got to do is to organize all the expressions appropriately. And look, now organize. Let's put all the expressions with cosine, all the expressions with cosine together, and all the expressions with sine together as well. So look, what we get here: a1 plus a2 cosine theta t. Then we add to it a1, this time minus a2, and we are remembering that expressions with sine over here and over here contain I. So we put I over here and write sine theta t. Okay, and we can close the brackets. And look, this brings us actually to the final formula for the complementary function of a second order difference equation in the case of complex roots. And it looks like that. Then yc is rt times a5 cosine theta t plus a6 sine theta t. And of course, in those circumstances, we need to remember that our a5 is simply equal to a1 plus a2, while a6 is equal to a1 minus a2 I. Now, this expression is what we are going to be working with in order to deal with in the case of complex roots when we're going to try to find complementary function. However, there is also a couple of new things in here. So now let's just do a couple of examples. Okay, so now let's move to examples. And we're going to start with this one. Okay, so look, what do we see over here? First, with this equation, we do not have yt plus 1. Well, this means that a1 is equal to 0. And 0 is definitely lower than 4a2, which is 4 times 1 over 4, or simply 1. In this case, we clearly see that we will have complex roots. And if we have complex roots, then we know what to do. First, we need to find h. H is negative a1 over 2. However, since a1 is 0, well, this must be 0. Then v, which is 1 over 2 square root of 4a2 minus a1, minus a1, right? So we got that this is 1 over 2 times 1 is 0, which is 1, so we get here just 1 over 2. And the last thing we need to take care of is what is r, and here we use the formula I showed you previously. This is equal to square root of a2, and as a2 is 1 over 4, square root is 1 over 2. Now, look, the thing about solving second order difference equations in the case of complex roots is then we need to have one additional piece of information that we didn't need before. And this piece of information is actually what is theta. And look, in order to find what is theta, we need to use the relationships, those interrelated relationships I've told you before. So look, first, cosine theta, in our case, of course, well, in general, right, we remember that this is h divided by r. And look, our h is 0, and because our r is non-zero, we see that cosine is 0, right? Definitely. Now, sine is equal to v over r. And look, in our case, actually v is 1 over 2, and r is also 1 over 2, right? So, sine must be 1. And look, now we need to use either what we remember from high school about trigonometric functions. We can look at their graphs, but the best way, of course, is to use trigonometric tables, where you can all find it. However, remember, in all the examples we're going to be giving to you in exams, they're going to be easy, really easy to find. So, now, our question is, for what value of theta cosine is equal to 0, and for what value of theta sine is equal to 1? Well, we know that sine takes 1 at pi over 2, and cosine takes 0 at pi over 2. So both of these conditions are met, right? So we can conclude that theta must be pi over 2. Of course, look, you can always add plus 2k pi. However, this is not important to us. This is the result that is enough. How we could add those plus 2k pi, we wouldn't just add anything. Okay, and look, I also showed you the formulas for this. However, all these formulas, you only use them when it's actually really necessary. If it's not, you can just skip it, right? Okay, so what do we do next? Now we are ready to find the complementary function, right? Complementary function is RT A5 cosine theta t plus A6 sine theta t. Right? So now, we've got r equal to 1 over 2 to the power of t, and then we start by a5 cosine pi over 2 t plus a6 sine pi over 2 t. Okay, now we need to find a particular solution, which is given in this case simply by c over 1 plus a1 plus a2, which in this case gives us 5 over 1 plus 1 over 4, or 5 times 5 over, divided by 5 over 4, which gives us 5 times 4 over 5, or 4. So the final solution, so the time path of y, in this case, is of course given as a sum of complementary function. In particular solution, so this is 1 over 2 t a5 cosine pi over 2t plus a6 sine pi over 2t plus 4. Okay, so look, the only new thing that actually appears over here is associated with the complementary function in the formula we use for it. Unlike before, we need to know what is the value of theta. So we need to use those relationships between h, v, because remember, if we know h, v, we can calculate r. With r, v, and h, we can easily find sine and cosine theta theta, and we can find value of theta. Okay, so let's just do one more. Now we have a homogeneous second order difference equation, so we don't need to find particular solution. All we need to do is concentrate on on complementary function. In our case, a1 squared is negative 4 squared, which is 16. And 16 is clearly lower than 64, which is equal to 4a2. Right? Again, we can be sure that we're gonna have complex roots. So we start by finding h. H, of course, negative a1 over 2 gives us 4 over 2, right? Because 1 is minus 1. So 4 over 2, we've got 2. Then we've got v equal to 1 over 2 square root of 4a2 minus a1 squared. In this case, we get that this is 1 over 2. 64 minus 16. So this is 1 over 2 square root of 48. This is the same as 1 over 2 times 4 times square root of 3, right? We can take 16 out of the square root, so we get 4. So this gives us 2 square roots of 3. And finally, what is r? Well, r being square root of a2 is equal to just 4, right? So now, again, we have enough information to establish what is theta. Why? Like, look, cosine theta, which is equal to h over r, is 2 over 4, 1 over 2, right? Then we get that sine theta is v over r, right? We know that v is 2. We know that it is 2. 2 square root of 3 over 4, which would give us square root of 3 over 2. And now again, the question, what must be theta such as cosine is equal to 1 over 2 and sine is equal to square root of 3 over 2? Well, again, we use just trigonometric tables, or we just remember that this means that theta is equal to pi over 3, right? Okay, so if we've got theta, we have everything that we need in order to find the complementary function. However, as this is a homogeneous equation, complementary function constitutes the full time path, right? So first, r to the power of t, then times a5 times cosine pi over 3t plus a6 times sine pi over 3t. Okay, so this is it. This is how we solve, how we find complementary function in second order difference equations under the case of complex roots. Okay, what are we going to do next is to see when our equilibrium is dynamically stable. Again, we will be able to use what we already learned in the case of second order differential equations and what we learned about first order difference equations. Combine this knowledge and we will be able to assess the stability of the equilibrium. Okay, thank you for your attention and see you in the next video.
video.